All right, so chapter 9 was all about aldehydes and ketones, and so we're going to start with where we usually start when we learn a new functional group, and that's nomenclature. All right, so I'm going to put down some compounds, and you tell me the names of these compounds here. All right, so aldehydes and ketones, and in terms of like the reactivity of these two functional groups, they're very, very similar, but we do got to sort of have these two separate categories in our brain because that's how we name these. So both of these on the left are aldehydes, so they're going to have this Al suffix, and on the right these are ketones, so they'll have that ONE suffix, okay? So this first one here, we got 1, 2, 3 carbons. So 3 carbons would be prop. So this is propanal. Okay, and remember with aldehydes, we actually don't bother to indicate the location because they're always on carbon 1, just by virtue of being an aldehyde, right? You got to be on one of those terminal carbons in order to be an aldehyde. So just propanal. Okay. For my ketone here, so same thing, I gotta find my parent chain. 1, 2, 3, 4, 5, 6. But for ketones, we do have to specify the location of that functional group. It is located on carbon 3 out of 6. So this would be 3-hexanone. Okay. Our next aldehyde, same sort of idea. We got to find our parent chain, 1, 2, 3, 4. We also have this carbon sticking off of it. Remember, our name's got to include all the carbons, so we're going to have this methyl group. Okay. We got our aldehyde functional group. We don't have to specify the location of, but remember, that's because we always assume it's on carbon 1. So you got to start counting from that aldehyde carbon. So 1, 2, 3. This would be 3-methyl butanal. But because my parent chain is 4 carbons long. All right, and then the last one here. Again, find our parent chain, 1, 2, 3, 4, 5, 6, 7. It's a ketone, so we're going to have to number our parent chain. We'll do it both directions, 1, 2, 3, 4, 5, 6, 7. Or the other direction, 1, 2, 3, 4, 5, 6, 7. And which numbering scheme are we going to pick, the red or the blue? The red, right? Because we're only going to focus on that ketone functional group. We're going to prioritize it to make sure that it has the lowest number. Okay, so I'm going to pick my red numbering scheme. I got these 2 chloro groups. Remember, you got to indicate the location of both of them, right? So it's not just 6, but 6, 6 dichloro. 3-heptanone. All right, so first thing we learned how to do was to name these 2 functional groups, aldehydes and ketones. Aldehydes, remember, you have your carbonyl group located on a terminal carbon. Ketones means that it's in the middle of the molecule. All right, necessarily having 2 carbons on, or a carbon on either side of that carbonyl carbon. All right, so first reaction of aldehydes and ketones that we covered was actually one we've seen before, and that is that Grignard reaction. All right, so now 2 chapters we've covered this, so it's a good indication that it's definitely going to be on our exam. All right, let's just do a quick example real quick where you guys predict the products of this Grignard reaction. right, so I should actually save this one because it's kind of on theme with some other reactions here, but we learned a few reactions in this chapter where we create a new carbon-carbon bond. And remember, that's always a little scary. We always get a big, ugly product on the other side. So it's really important to sort of break it into steps and make sure that you're connecting the correct carbons. So in this case, I'm going to connect the carbon that's at the base of that carbonyl group, my carbonyl carbon, with the carbon that's bound to the magnesium in my Grignard. This is where my new bond has to be in my product. So when I'm going to start drawing my product, I'll go ahead and start with these 1, 2, 3 carbons from my aldehyde. Okay, so then if this is my orange carbon, I'm going to draw that new bond, and on the other side has to be that Grignard green carbon. So then I just need to make sure to include everything attached to that green carbon, right? So it's got these 1, 2, 3 carbons on there. So here's green. Got 1, 2, 3. All right, and then lastly, let's include that functional group for our Grignard product, which is what? What's my functional group? The alcohol, the OH group. All right, and so that's what my carbonyl oxygen used to be, a carbonyl oxygen, and now is an alcohol oxygen. All right, but again, we can go back and double check, make sure we got the correct number of carbons. So I got 1, 2, 3 from my aldehyde. Those are those 3. And I have 1, 2, 3, 4 from my Grignard. 1, 2, 3, 4. Boom. What's up?
All right, so this one doesn't matter. Okay, would it matter about the structure, or as long as your carbons are right?
So, all right, like just to be clear, you drew it like pointed up like that or something. That's the exact same thing, right? You can really rotate about any one of these single bonds. So I could also sort of draw it like this. It would look super weird, but that's also the same, right? I got the same number of carbons, and I have my new bond is in the correct place, right? Between this carbon and this carbon. The correct carbon from my Grignard and the correct carbon from my aldehyde. Was that more or less your question?
Yeah.
Right, so the orientation of those single bonds in space don't matter because you can always rotate about it. If you imagine building one of those model kit structures and then just kind of taking it and kinking it, that's how like all of these structures here are equivalent. They all have that same correct connection.
Yeah, because what I did with the OH, I stuck it up, so instead of going down, I just kept going, and then I connected it bottomwise.
Yeah, so like this, and then like that. Oh wait, that's not quite right. Like that is also the same thing.
Okay.
Absolutely. All right. I really should have. Let's take a step back. We got these reactions that create these new carbon-carbon bonds. Let's actually knock out the other ones first. These sort of one-step kind of things that we can do with our aldehydes and ketones. So let's just go ahead and put one aldehyde in the middle here. I don't know. We'll do this thing. And we got a few things we can do this. So let me actually make it a little smaller. All right, so we learned about a few reactions of aldehydes and ketones. Let's start with this one here because this one's kind of the odd one out. This PPH3 business, this lets us know that we're talking about a Wittig reaction. Wittig is the scientist that it's named after. And this will create a new carbon-carbon double bond here. Okay, so we're going to replace that carbonyl bond. So I'm going to start by redrawing my aldehyde. Okay, but my new, my carbonyl double bond, carbon-oxygen double bond, is replaced by this new carbon-carbon double bond. That is highly annoying. Okay, so I have this carbon now on the other end. I just got to include that one extra one sticking off. All right, so I have those 2 carbons from my Wittig in my product, from my Wittig reagent. All right, and again, the whole thing about this Wittig is that we have this new carbon-carbon double bond that's formed. Okay, all of these other ones are pretty closely related. This thing that we've seen before, and again, anytime you see chromium, you think what? Oxidation. All right, and in fact, this is our strong oxidizer, which will convert a aldehyde into a carboxylic acid. So add that extra carbon-oxygen bond there. Right, doesn't change the number of carbons, just inserts a new carbon-oxygen bond. All right, and then the BH3, what's called borohydride, is the exact opposite. This is a reduction reaction. So oxidation reactions create more carbon-oxygen bonds. Reduction reactions do the opposite. It's going to reduce the number of carbon-oxygen bonds that we have. So in particular, it's going to take this carbonyl group here and reduce it to just an alcohol. All right, and then the last one here, I have a little question mark on my arrow. We need to fill in the missing reagent here. If I'm starting with an alcohol and I want to go the other direction, I want to go to an aldehyde, what type of reaction would that be? Yeah, the DMP, and what category, right? That's also an oxidation reaction, but we needed to use our weak oxidizer. And yes, that would be, there's 2 of them that we know about. They both have those 3-letter abbreviations, DMP or PCC. Okay, so we got a lot of oxidation reduction reactions surrounding our aldehydes and ketones. Don't forget about this kind of weird oddball out here, these Wittig reactions that create those new carbon-carbon bonds. And again, the Wittig, you can sort of, the signature there is that PPH3 business, right? Whatever is on the other side of that is what's going to end up being attached to that carbonyl carbon. Okay, so let's just do one more Wittig here. Make sure we got this down. All right. So I'm going to create my new carbon-carbon double bond here. Again, it's that carbonyl carbon. That's always sort of the active site of this particular functional group, right? That's where my new bond is on my carbonyl. And then the thing at the base of that PPH3 business. So there's my new carbon-carbon double bond. Here I'd actually be able to draw two separate products that are different because of the stereochemistry of our double bonds. Let's look at these two and see if we can't figure out which one should be our actual product here. So I got 1, 2, and then my branch. Oops. Okay, so we could put it on that side, or I could put that fork on the other side. Okay. Just sort of remembering our double bond stuff, not for exam 3, because it's not something that I'm going to be testing you on exam 3, but certainly something that will be on our final exam is this EZ nomenclature for our alkenes. So sort of on your own, you can convince yourself that this would be the Z conformation here, and this is the E conformation. Okay, and so just looking at these two here, let's see if we can't figure out which one. You would get a mixture of both of these, all right, but one of these is actually going to be your major product. Let's take a vote here. Who thinks it's going to be the Z conformation? And who thinks it's going to be the E conformation? And who has absolutely no idea what we would be looking for here? All right, so the whole thing is that what's the one sort of rule of in general when it comes to the stereochemistry is that big groups do not like to be next to each other, right? It's less stable to have these big chunky groups on the same side of the double bond. So you're always going to want to put your smaller group with that big group, right? The E conformation is actually going to be not crazy, but going to be the major product, because the Z conformation has this big group and this big group both on the same side. All right, so more stable is less sterically hindered. All right, so this thing over here where the smaller end is on the same side as that big chunky fork thing. All right, so that's what would make this our major product and this our minor product. Okay.
Should we just pick one of these in the exam?
So either one of these would be worth a heck of a lot of credit, but yes, you would lose 1 point if you gave me this one versus this one, right? Because that major product is going to have, again, is less sterically hindered.
But even if you don't specify, like, oh, draw the major product?
I will specify draw the major product. All right, so last ones that we're going to sort of review here. Again, let's revisit that Grignard reagent again, because we did that one a lot, and we see some similar features in our aldol condensation reaction as well. So let's just do another review of a Grignard here. All right, so again, we got to figure out where a new bond is. Our carbonyl carbon and the one bound to that magnesium. So that's where my new bond is going to be. So my product, I'll start drawing those 5 carbons from my ketone. So that middle one, that's my carbonyl carbon. So I'm going to draw a new bond, and that's going to be my Grignard carbon, my green carbon. So I just need to include the other 1, 2 on the end of that one. Oops. So 1, 2 more, and that alcohol functional group. Boom. Okay, and again, that carbonyl oxygen becomes an alcohol oxygen in my product. All right, I get this new carbon-carbon bond. I guess we can double check, count carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Plus 1, 2, 3. 1, 2, 3. All right, so we have this new carbon-carbon double bond. And again, that oxygen that used to be my carbonyl oxygen is now my alcohol oxygen. All right. And the reason that we want to make sure we have that down is because that's going to be something similar that we see with these aldol addition reactions. Okay, so if I just put down, we'll do an aldehyde here. Remember, if we toss in a little bit of base, some sodium hydroxide, we'll get these aldol condensation reactions here. Everybody take a second and see if you can't give me the product.
This is an alcohol?
Yeah, this is an aldehyde. If it's just an aldehyde or ketone with some base, some sodium hydroxide on there, it's an aldol addition reaction. All right, and just to remind you, these are between neighboring aldehydes and ketones. So one of the best things to do to help you visualize the product is to redraw a second copy, of that propanol underneath so you can see how these two molecules should connect. All right, so again, these are called aldol addition reactions. All right, and what I'm going to do is I'm going to make a copy of my aldehyde, because these are, again, they're going to be taking place between neighboring molecules here, right? If I have a beaker of this thing here, I don't just have one molecule like in our pencil and paper chemistry. I have a bajillion of them, all right? And so these aldol additions, I'm going to be creating a new carbon-carbon bond between the carbonyl carbon of 1 and what we have a special name for the other carbon, this one here in my neighboring molecule, the alpha carbon of its neighbor. This is where my new carbon-carbon bond is going to be. So I'm going to start by redrawing those 1, 2, 3 carbons from my original aldehyde. That's this one there. I'm going to go ahead and draw my new bond. I'm actually going to sort of orient this to try to make it a little bit easier visually to see how these things are connected. So when I draw my new bond, that's my alpha carbon of its neighbor. All right, so then I'll put in those 1, 2. Okay. Importantly, the carbonyl group of this green fragment doesn't get touched at all. It's not in the reaction whatsoever. So that's just going to appear as is in my product. All right, this is from my alpha carbon fragment there. But the orange fragment, that carbonyl carbon is involved in that reaction. So just like in our Grignards, throughout the course of that reaction, it gets converted into an alcohol group, into a hydroxyl group. Okay. The alpha carbon component, this one was my nucleophile. The carbonyl carbon fragment is our electrophile in these reactions. Okay, and for these reactions in particular, we had this sort of double check that we can do when we draw our product. And that is those two functional groups are always located the same number of carbons away from one another. So we can sort of have this extra double check to make sure that we've linked these things up correctly. If I start counting at my carbonyl carbon towards that alcohol, my new bond is always between carbons 2 and 3, right? So it's just an extra double check that you can do. You know, in addition to counting carbons, making sure we have the same number of carbons on both sides, that's a double check we can always do with our reactions. For these ones in particular, we can make sure that our new bond is in the right place using this sort of counting method here, starting at our carbonyl carbon and counting towards our alcohol carbon. All right, so for the sake of sort of time here, we'll take the same one. And what if I gave you that same NaOH, but then I said there was also heat in there? What would be your product then? All right, so the heat lets us know that we're talking about an aldol condensation. So I'm still going to connect these the same way. Carbonyl carbon of 1, the alpha carbon of its neighbor. All right. right? So I'm just going to redraw our addition product here. All right. This would be our addition product, but what's different about our condensation, we have this same sort of aldol addition reaction, but it's the addition followed by what's called a dehydration, which is where we're going to lose this alcohol group and a hydrogen from this carbon here and form a double bond. Our alkene is our dehydration product, so boom. Okay, so we can still sort of play the same game. We got the same number of carbons, 1, 2, 3. One, two, three from my alpha carbon fragment from my nucleophile. All right, but now we have this new carbon-carbon double bond that forms as a result of that dehydration reaction. All right, good news here is we can still do that same sort of counting carbon double check where we start counting at our carbonyl carbon. 1, 2, 3, and again, that new bond, now it's a double bond, is located between carbons 2 and 3. All right, so if there's no heat, we know we're talking about an aldol addition reaction. If there's heat in there as well, that's going to be the condensation reaction. All right, and then the last one, same sort of type of reaction here, but this would be what we call a mixed aldol condensation. So let's say that I take this thing, and the first thing I'm going to do is treat it with LDA, and after I do that, I'm going to mix in some propanol. What would my product be? All right, so this is the same type of reaction, but what this does is allow you to create one specific sort of product, because you get to select which one of these is going to play the role of the nucleophile and which one's going to play the role of the electrophile. So the one that you treat with LDA first, this is your nucleophile, right? Which means that the alpha carbon of this, 3-propanone is going to be involved in this reaction, right? That component that we treat with LDA is our nucleophile. The other component is then the electrophile. And remember, our electrophile is the one where the carbonyl carbon is our reaction site. So this is how I'm going to link these two together. I will get one specific product out of this by treating this first with LDA. That makes that our nucleophile in this reaction. Okay, so I'm going to start by drawing these 1, 2, 3 carbons from my propanol. when I draw that new bond, on the other side is that alpha carbon. So then I can just put in those other ones. What's the one thing that I'm missing here? The alcohol. And is it an alcohol or a double bond? Do I have heat here? No, right? So in this case, it's just that addition product, just that alcohol group. If I did have heat listed under here, then I would do my condensation reaction. Then I would have that double bond that's formed. All right, but we can just count carbons, make sure we get the same number. 1, 2, 3, 1, 2, 3. And then from my nucleophile, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And again, specifically for these reactions here, we got that extra check where we can make sure everything's connected correctly by counting from our carbonyl carbon to our alcohol carbon. And we see that our new bond is between carbons 2 and 3. Cool. All right. Awesome. So, just got some examples.